Welcome everyone. Let's go ahead and get started with today's ETAP Digital Twin presentation. But first, a brief background on ETAP, the company. ETAP is the global leader in electrical power systems, providing innovative solutions for modeling, design, analysis, optimization, control, and automation. Headquartered out of Irvine, California, but with multiple offices globally, supporting the needs of electrical engineer professionals all over the world. Our engineers, scientists, industry experts, and professionals are present in over 50 ETAP offices around the world, providing state-of-the-art products with the highest standard in quality to over 10,000 clients worldwide. ETAP has a variety of solutions for powering the world, with a strong presence in the following sectors. Generation, from conventional and nuclear to renewable energy and microgrids. Transmission, distribution, from co-ops to Tier 1 utilities all around the world. Industrial, from manufacturing, metals and mining sites, to oil and gas, both offshore and onshore. Transportation, railways, airports, to marine shipping. The low voltage sector, from mission critical facilities, data centers, to other commercial facilities. And every one of these sectors is currently undergoing a digital transformation. And today's presentation will illustrate ETAP's solution for this transformation. The ETAP Unified Digital Twin provides an environment, essentially a digital representation of the electrical power network and major assets in it. You could think of it as it is the active blueprint for every stage of the system's life cycle, from design to operation to automation. Here is a typical system's life cycle. The ETAP Digital Twin is the single platform for design, operation, and smart automation, and the key value is the model-driven approach. I will emphasize a little bit more regarding the model-driven approach throughout the presentation. Let's begin by going over the powerful design and capabilities available. I will now switch over to ETAP to create a one-line diagram using AutoBuild. The creation of a one-line diagram using AutoBuild, where the engineer can quickly develop a one-line diagram by simply selecting the desired elements found on the right-hand side toolbars, both AC and DC elements, and allowing ETAP's powerful rulebook to automatically connect and align the entire system. So I will simply select the element and allow the program to automatically do the connection and alignment of the system. So here we have the main incoming or point of common coupling point to the system. It is at 13.5 kV. It is fed by an overhead line, transmission line, and it feeds a 2-winding transformer, step-down transformer from 13.5 kV down to 13.8 kV. It goes through an underground thermal and underground cable. This then feeds several medium voltage buildings, feeding also a large pump, which is represented as a synchronous motor, and then stepping down the voltage from 13.8 kV to 480 volts. It's another transformer feeding an MCC. This motor control center will have 4 480 volt motors, and we can actually also use AutoBuild to provide or enter the protected device using the rulebook. After the connected single line diagram has been generated, the engineer would then double click on each element and enter the rating and the nameplate information as shown up on the screen. Now, for utilities and other sectors like railways, the engineer may choose to import the grid network data from an existing GIS database like Esri and generate an intelligent ETAP model with connectivity and all impedance information. This is necessary due to the vast number of circuits, loads, transformers, and other elements that may take months to generate if it was done individually by hand. On the center of the screen is the ETAP geospatial view of the grid imported from an existing ArcGIS database. The connectivity and all impedance information is automatically imported and brought in from the GIS database. On the left side of the screen is the OLV, or logical network view. This is commonly used by the protection engineer to look at the radial representation on main feeders, to set protection, create time characteristic curves, and also display other results such as incident energy or voltage drop, maximum available fault. On the right hand side of the screen, it's another view called the network view. This view provides the engineer and operator a clear view of the entire distribution network. With multiple views, planning engineers have all available views at their fingertips for quick visualizing and performing analysis, displaying study results right on top of the view. A successful digital twin begins with a strong design foundation. Design includes both modeling tools plus analysis modules. ETAP provides an unmatched modeling platform that includes tools for field data collection and smart data entry. Engineers and anyone collecting data can make use of the data collection app or Excel import-export when managing large amounts of data collected. The ETAP data collection app does not require an ETAP license, and it can be installed on either an iPad or a Microsoft Surface tablet. Once the engineer has collected the data on the data collection app, it can then be transferred into a commercial ETAP license. For projects with tight deadlines, engineering teams can more efficiently model and simulate entire networks by entering data into a model. This greatly simplifies project management by collaborating or working in parallel from various remote locations. So you could have an owner-operator host the master ETAP model and then assign different engineers a scope of work, as well as allowing outside consultants or contractors to take control of modeling a section of the system. They would then in turn check in the results, and the owner-operator or the designated administrator would review those changes and either approve, reject, or comment on the changes. All of this simultaneously running analysis and generating reports, all while keeping a single centralized database model. With the built-in multi-dimensional database, users can model various operating scenarios and switching configurations to fully investigate and study the behavior and characteristics of the electrical network using one unified database. This comes extremely handy for those projects such as performing an arc flash analysis, when the engineer is required to take multiple operating conditions into account, run arc flash for each operating condition, and select the worst or the highest incident energy to produce the labels. This is also true when performing cable sizing, where you may have multiple operating conditions and main transformers that are in or out of service due to maintenance. Cable sizing is compliant with international standards and provides various options that can be used for design requirements. These requirements can be user-defined or automatically populated from load flow, short circuit, or protected device calculation results. For detailed information on the cable standards that are supported, please visit the website. The library data is verified and validated based on the latest manufacturer's published cut sheets. This includes all kinds of protected devices that are part of the ETAP library, such as relays, both electronic and electromechanical, low voltage circuit breakers from molded case with electronic trip units to thermal magnetic devices, fuses, cables, overhead lines, to name a few, to provide users with the most accurate results on their model. There's even a harmonics source library that will include various manufacturers based on VFD drives or other elements, as well as typical IEEE harmonic source libraries. As mentioned earlier, a successful digital twin begins with a strong design foundation. Design includes both modeling tools plus analysis tools. Let's take a look at the analysis tools. Using a unified multi-system approach, engineers have the ability to perform simultaneous AC and DC analysis. This is extremely useful for those projects that have renewable energy present and have both AC as well as DC. Network analysis is at the core of ETAP. A strong network analysis foundation is essential for accurate protection and coordination studies. It is also essential for electrical safety, such as shock and grounding, to arc flash analysis. Design and optimization analysis, such as underground cable thermal analysis for safe feeder operation, to power quality optimization, such as harmonic analysis and filter design. Dynamics and transients, for performing transient stability studies by simulating multiple possible system disturbances, or to validate existing microgrid and load shedding controllers. With multiple auto-run and study wizard and Python scripting, ETAP allows engineers to automate running multiple scenarios, which minimizes human error, and also it provides a powerful platform for grid code compliance studies. And finally, a powerful unified AC and DC modeling and time series power flow analysis for renewable energy and distributed energy resources projects. Going into a bit more detail on each, let's take a look at protection and coordination analysis, which provides the protection engineer with the ability to automatically check existing protected device settings based on industry guidelines and standards. These guidelines are automatically included in the rulebook are taken from standards such as IEEE, IEC, NEC, and other local standards. Also, the ability to simulate sequence of operations by graphically showing trip devices operate in the event of a fault. This provides the protection engineer with the ability to visualize the sequence of operation based on a single line to ground fault, a three-phase fault, a line-to-line ground, etc. And it supports from distance and directional relays to overcurrent and thermal devices. Moving on to safety and arc flash. Full compliance with the latest IEEE 1584 standard and solutions such as energy boundary area plugs, which is a unique probabilistic approach tool for calculating incident energy safety range that takes into account tolerances in enclosure area or volume and electrode configuration. This is extremely useful on IEEE 1584 2018 standard, since we are now responsible for collecting enclosure area and electrode configuration. Very useful for design engineers during a front-end engineering design project when enclosure dimensions and electrode orientation may not be available. This optimizing protected device settings and boosting productivity and safety. And for those locations with voltages that are outside the IEEE 1584 standard or above 15 kV, the high voltage arc flash module will provide highly accurate results. It is important to mention that assumptions must be made during design. This means the design model is usually generated with minimum and maximum loading and generation values, and for very good reasons. For producing conservative results when doing equipment sizing, voltage drop, fault analysis, arc flash, device duty evaluation, etc. However, for running the design model using actual operating values from the field, we require real-time data. The operation model makes use of the existing design plus real-time data, which is actual loading and generation values, as well as power flows and switching up operating status. State estimation. This is built into ETAP for helping users tune the design model and provide intelligent alerts and monitoring at central locations where metering devices are not present. And when available, load allocation information. Once the design model of a system is brought into operation, it can be used for monitoring. It could also be used to operate and manage system, for predictive simulation and control. Multiple solutions are available for each as listed here. A state-of-the-art model-driven electrical SCADA with powerful state load estimation built in that provides intelligent alarming by allowing the monitoring of locations that are blind to legacy SCADA or monitoring systems. Our model-driven SCADA is able to monitor these locations by making use of state estimation, providing automation engineers the ability to create intelligent alarms on these locations. It is also extremely helpful as a root cause analysis tool, as it can also play back past or historical disturbances in a system to better understand system behavior and prevent future outages. For those of you who have ever performed a coordination study, I'm sure you understand the huge amount of work that is required on collecting existing protected device settings from the field. Well, what about using your existing model as a centralized relay and asset management tool? Just think about being able to connect your ETAP model to the system and retrieve existing protected device settings. Or, after performing a coordination study in ETAP Star, you can increase the data quality by automatically pushing or sending the validated relay settings directly to the devices. eProtect also supports automatically generating relay settings files. Operator Training Simulator. For utility and industrial applications that require operator training simulator, this solution makes use of ETAP software in a loop to realistically simulate an existing network. It could be used to train operators on operating a SCADA, a power monitoring system, an EMS, a microgrid, and also an ADMS system. And finally, to complete the digital transformation, the cornerstone model is automation. The automation model has a higher level of awareness as how the system will react. It provides proactive action rather than simply reacting to events after they happen. And it contains intelligent applications to provide predictive system simulation, optimization, and automation. The automation model has on-demand predictive analysis, situational intelligence, proactive simulation results on alert, or alert engineer of immediate problems. Proactive alarms based on other conservative, alternative, or future actions. And optimization capabilities such as volt-var optimization and control to minimize distribution losses and track performance. This solution takes into account not only load tap changers on transformers, but also capacitors that are on the field, photovoltaic inverters, and voltage regulators. Providing real-time optimization and energy use tracking. Switching optimization. It provides optimal status of existing switching devices and suggests locations for new type open points in the system. It can also be used by the design or operating engineer to minimize system real losses and reduce or eliminate abnormal operating conditions. Automatic Generation Control, or AGC, to calculate the required demand or make changes to optimize generation. And it takes into account real-time data, such as frequency and actual generation. Automation controllers optimize with model-driven logic such that system behavior has already been established and can be predicted, so that as triggers are generated in the system, such as a network disturbance, the controller is able to instantly provide the right commands. Controllers include intelligent load shedding, plant controller, and substation automation controller. The microgrid controller is also model-driven and preloaded with intelligent automation and system protection to optimize and control battery energy storage, photovoltaic inverter controls, generation and frequency control, demand side management. The ETAP digital twin benefits include design, operation lessons, analytics, intelligence, and optimal planning. These all to accurately analysis with actual operating values, improve system planning and design, recognize and correct potential hidden problems, prevent system interruption, other benefits of ETAP digital twin includes accurate analysis, determine underutilization of system resources, identify the cause of operating problems, accelerate engineer and operator training, virtual test of operator and controller actions, and validate system settings. Thank you everyone for your time.